4.1 Glucose can decompose in the presence of microorganisms from a range of products. One of these is a carboxylic acid with the relative formula mass of 88, and it contains 40.9% carbon and 4.5% hydrogen by mass. If you add up 40.9 and 4.5, it doesn't come to 100%, and that's because a carboxylic acid has got oxygen in it as well. So the first step to do is to work out what percentage is left over, and that must be oxygen. So the percentage of oxygen is the 100%, take away the 40.9, take away 4.5, and so 54.6% is oxygen. Your next step to work out how many atoms of each there are as a ratio is to take each of the percentages and divide by the relative atomic masses of each of the atoms. So 40.9% divided by 12, which is the mass of a carbon atom, comes out as 3.41. 4.5 divided by 1, a hydrogen has an atomic mass of 1, is 4.5, and 54.6 divided by 16 is 3.41. So oxygen has got an atomic mass of 16. So that comes out as 3.41. Now, the problem is you've got to try and get these as whole numbers. So the easiest way to do that is to divide through by the smallest number. Divide all of them by 3.41. So if you divide all of them by 3.41, 3.41 becomes 1. That at least gets one whole number. 4.5 divided by 3.41 unfortunately comes out as 1.32. And 3.41 here becomes a 1. Now you've got to multiply up then to get this one to be a whole number. That's nearly 1 1/3, 1.33. So if I multiply by that by 3, it's going to become 4, more or less. That one by 3 becomes 3, so 3, 3, 3, 4 and 3. So if I multiply each of them by 3, I'm going to end up with 3 to 3.96. Let's call it 4. It's an experiment after all. We can say 3 to 4 to 3. Okay, now then, if I had C3H4O3 and I add that up, so a carbon's 12, so 3 12's 36, add 4 1's, add 3 16's, it comes out as 88. And it says here that its MR is 88. So 343 is its molecular formula mass. So the molecular formula 88 is C3H4O3. The relative formula mass of 88 matches that. Therefore the molecular formula is the same as the simplest formula, 3 to 4 to 3. Write an equation for the reaction during fermentation. Well, you've got to know what glucose is for a start. You must know that glucose is C6H12O6. If you don't know that, you can't do that. You've got to know that during fermentation you make ethanol, and you've got to know that ethanol is C2H5OH, and you've also got to know that it makes carbon dioxide. If you don't know the formula of those three, and that glucose makes ethanol and carbon dioxide during fermentation, then you can't complete this question. The next part is that you've got to work out, you've got to balance it basically then. So what have I got in here? Well, the first thing I would look at is that the ethanol is the only product with H's in it. The CO2 doesn't have H's. So how many H's have I got in my ethanol? I've got 5 and 1 is 6, and I've got 12 H's. So that must be a 2. There's got to be a 2 in front of that, because 2 multiplied by 5 is 10, and 2 ones are 2 to make the 12. That's got to be a 2. So 2 carbons, 2 2's are 4 carbons. I need 6. That's got to be a 2 as well to balance the carbons. 2 times 2 is 4, times 2, add 2 times 1 is 2, 4 add 2 is 6. That will do it for me. Therefore, 06, 2 in front of that, 2 1's add a 2, 2 4's gets the oxygen as well. So there we go, that's going to balance that equation. Suggest one advantage and one disadvantage for industry of carrying out the fermentation at a higher temperature. So the fermentation is carried out at 35 degrees C rather than 25 degrees C in industry. Why would you do that? That's because you're going to increase the rate of the reaction. You're going to make the ethanol more quickly. So the ethanol is produced at a faster rate. One disadvantage is that you're going to need more energy. You're going to have to do it at a higher temperature, so it's going to use more energy. 4.4. The method used in 4.2 would result in the ethanol being contaminated by ethanoic acid. Why? Well, ethanol has got an OH bonded to a C, which is bonded to one other C. So the COH in ethanol, the C of the OH, the C bit of the OH is bonded to one other carbon. We call that a primary alcohol. A primary alcohol like ethanol can be oxidized. So it can be oxidized and it will turn into ethanal, which is an aldehyde, and then it will further oxidize into something called ethanoic acid. Now there's a few ways that you can do that. You could add something like acidified potassium dichromate, which would go from orange to green and would do that. You'd have to heat it up, a process called reflux. But the other way that you could do it, it would also react with the air quite slowly, but it would oxidize in the presence of air, and the ethanol, a primary alcohol, would turn into an aldehyde, ethanal, and then into ethanoic acid. It looks as if the air's got in. Give two differences between the infrared spectrum of a carboxylic acid and that of an alcohol. Well, a carboxylic acid has got a C double bond OH on it, and an alcohol has just got an OH. But the spectra are different for a carboxylic acid's OH and an alcohol's OH. So an alcohol OH absorbs infrared light at a different place, a different frequency from the acid OH absorption. In other words, you get an absorption peak for an OH of an alcohol at a different place than you get an absorption peak for an OH on a carboxylic acid. And it's always worth referring to and writing the numbers down from your data book. The second one, of course, is that a carboxylic acid has got a C double bond O in it, and an alcohol hasn't got a C double bond O in it. So the C double bond O in acids has an absorption peak, and again, quote the numbers.